Interesting. Feels amazing, man. All right, I'll keep this as a list of things to obtain. All right, topology. Hold on, I want to check something really fast. Did I get anything from Jack? No. Okay. Topologies. All right, well, somehow I've actually graded everyone's daily homework already. Feels pretty good. You should be happy that I chose to take myself away from watching Vagabond for long enough to actually grade those this morning. Great show, by the way. Highly recommend it. All right, so wanted to make a couple of comments to start. So one, I'll have the test graded soon. I had a nice key already written up that I kind of want to not write up again, but my friend who mailed me the topology folder I left in Virginia still hasn't gotten here, and I'm wondering if he gave it to the right address. So may just have to take the hit and just do it. But yeah, that'll be done soon. And then wanted to talk projects. I realized that just posting the projects wasn't going to be that useful because a few of the terms we haven't really talked about yet. Which, I mean, that was also true for group theory because like we still hadn't hit quotients, I think, by the time that I was assigning those. But here there may be a few too many things. So my goal was post those hopefully by tonight, and then maybe at the start of class Thursday we can just kind of talk about the projects for 10 to 15 minutes and just kind of say like, okay, this is kind of what the idea. I mean, I'm going to give blurbs, but there are going to be some words that you don't really know the definitions to yet. So that's kind of the idea there. Just talk about those a little bit, see what interests you. And then hopefully, choose that over the weekend and we can kind of get started and have a little over a month to really get after the project. And so it doesn't feel like it's rushed. Okay. Does that sound like a plan? Cool. All right. So let's do some topology. All right. So today, like I said, I mean, I've already given feedback. If you did see that, if you didn't, that's also fine. So started with projection maps, right? So let me get my book on the right page because I have it ready for the next one. So projection maps are exactly what you would think, right? So you're going x cross y, and you just kind of pick the one, right? This to x, and it's exactly what you think. And pi 2 is defined similarly. We should be used to these, right? We saw them with vector spaces. We saw them with Cartesian products for groups. Projection maps kind of just exist anywhere you have products. And so, what the heck is that about? All right. So the thing that we wanted to do is show that this is an open map in general. So we need to define an open map. And so open maps and closed maps show up a decent amount in topology. We won't deal with them a ridiculous amount, but basically one way to define a homeomorphism is a continuous map that is also open. So basically continuous invertible map that is also open. And so we're going to get to continuous maps pretty soon, right after the quotient topology. And basically it all has to do with the images and pre-images of open sets. So start getting used to dealing with functions and how their images and pre-images work with these guys. Right, so we say that in general f from, I don't know, sure, x to y is open if for any u open in x, f of u is open in y. Okay, and pretty straightforward definition. So the thing that I was noticing a lot when I was looking through this, and it's not very surprising, is that we are really only dealing with the basic open sets, and you weren't starting with arbitrary open sets when dealing with the product topology, right? So the next one, I mean, we want to show, right, that, and it suffices to show it for one, but basically we wanted to show that from x cross y, sorry, this projection is open, right? So this is what we wanted to show in 160. And I mean, you had a reasonable starting spot, right? You wanted to take an open set in x cross y, but what does a general arbitrary open set look like in x cross y? So if I say U is open in x cross y, what does that mean about U? What is an arbitrary open guy? Um, kind of. What do you mean by that? The set of x's and set of y's? I don't think we need to like go down to the points necessarily. Right, yeah, U is open in the product. No, it doesn't lie in either of them. Mm, not exactly. So, our product topology. Okay, so not necessarily. So this is the mistake I was seeing. Okay, so the product topology, the open sets. Can you mute, please? Are not U cross V, or here, I'll use different letters, yeah. U1 cross V1, where U1 is open in X, and V1 is open in Y. That is your basis. These are just your basis elements. Okay, so a general U that is open is not necessarily the product of open sets. It is the union of products of open sets. Right, this was the whole, okay. It does not. So this is something we talked about last time with the rectangles, right? So if you take, let's just do 0, 1 cross 2, 3, sorry, 0, 1 cross 0, 1, union 2, 3 cross 2, 3 is in black, and then in red I will do 0, 1 union 2, 3 cross itself. Right, so this is, I have this guy, and then I don't know why it shows 2, 3, whatever, so it's like up here. Right, so this would be the thing in black, and then in red you get those, but you also get 0, 1 cross 2, 3, and then you get 2, 3 cross 0, 1. So you're getting extra stuff. These are not equal. Does that make sense? Right. So this was exactly looking back, this was 154 basically. So we don't need that, right? This is all about the map. So I mean, I just want to start with a U. I know it looks like this, and then I just need to show that once I apply the projection, I get an open set. So I need to look at pi 1 of U. And this is pi 1 of the union over the alphas of U alpha cross V alpha. And then if you looked way back in chapter 0, and I think I said that in our assignment, maybe I didn't and forgot, but I tried to at least think of that it should be useful to look back at chapter 1. Yeah, the skills you use. Yeah, I didn't say anything. Okay, that's fine. Yeah, so basically, how do maps work with these? So if you look way, way, way back, I think I said 27 is useful later on, or something like that. Yeah, so 27, if you look way back, we see that maps distribute over unions. Images and pre-images do. Or maybe it's not, sorry, 25 for maps. Pre-images is 27, and that's one I cite later. Okay, yeah, so 25 is basically that this guy would give us the union of the images. And you can check that. I mean, we did prove it way back, but it's not that hard to see. And so basically, once you do this, well, pi 1 of the U alpha cross V alpha is just U alpha, right? So we have this, and these are unions of open sets in X. So this guy is open in X because that has its own topology, and so it's closed under arbitrary unions. At the bottom of 25, it is important to note that the first two statements are true for arbitrary unions and intersections as well. This fact will be used later, right now. Yeah, so 25 and 27 both for intersections and unions work for arbitrary. And it's the same proof. Yeah, it's pretty straightforward. Yeah, so this is the key. And so, I mean, but basically you had the right ideas if it was the basic. You just needed this union part and basically using the fact that the image will distribute over it. Okay. So, oh yeah, sorry. So the product topology, it's no, so it's not necessarily that the components themselves have to be open. It's that you like don't necessarily have a nice way to describe the components. So I mean, it really is this in the product topology, like an open set. Like these are our basic opens, the blue guys that are circled, and then as usual with a basis, we just take a union of basic opens. So it's a union of things that are open in each component. No, but again, but the component of the big thing is not the union of its components, right? Because like this, look at this example again, right? Like, yes, U alphas and the V alphas are going to be open themselves, but like we would only get the thing in black here. This doesn't have like components that easily break down. It has to be written as a union, and that doesn't distribute. Okay. We can talk more later. That didn't sound like a satisfied okay. Sounds good. Okay. Suppose V is an open set in Y. So, okay. So this one is super important moving forward. So the pre-images are really the things that will define a lot of what we are doing. So we'll see this also in the quotient topology, where we're really defining open sets by their pre-images being open, and so this is really nice. So V subset of Y is open, then its pre-image under the projection map, I shouldn't say what that's equal to yet, is open in X cross Y. Right, so again, this is not a function, right? Pi 2, I mean, projections in general are very, very far from 1-to-1, right? I mean, these are, we're squishing down an entire segment. So unless that's like literally 1 point in X, then this guy is not going to be 1-to-1. So if we're looking at this, X cross Y to Y, then this is just the pre-image. So it's the things little x cross y such that y is in V, right? That once we map using the projection that we land in V. What is this set? More generally, or concisely, I guess. Yeah, this is just x cross V. And for those who aren't in our Discord, I'm not just talking to myself, I promise. All right, so yeah, this is just x cross V. Well, V was given to be open in Y, right? So this guy's open in Y. And X is most definitely open in X because, well, it's a topology and it's the whole thing. And so this is not only open, but in fact a basic open set in X cross Y. And so this is nice. So this is basic open in X cross Y. We don't need basic, but I just wanted to point that out. Discord is... what if it wasn't? I mean, isolation gets to us all, right? I'll probably be talking to myself quite a bit pretty soon. Yeah, so this is open. We're good. We got what we wanted. Good memes. Okay. So now if we define, and by the way, this is a good time. I can't remember how much we've really talked about this before. I don't think we really use the product symbol too much in group theory. But if I write this, right, this is my shorthand, similar to the big capital sigma for sums. This is the thing for products, so the capital pi. So this is just a nice concise way to write x1 cross x2 all the way down to xn. And I saw most people answer the projection map. How do we define the product topology here? What is x1 alpha? Okay, yeah, I'll use different notation because I don't like the double subscript, but sure. Yeah, and yes, exactly, those are basics. Bro, just give it a different name. You could. But why? Because mathematicians everywhere will hate you. Aren't you looking to get a computer science PhD? What do you mean, physicist? Yeah, so it's just this. And yeah, as Nick said, this is a basis, not the whole topology, right? So we can do unions of these things in the same way that we did before. Rippy has been muted. Nice. Yeah. And then our pi I, maybe I'll say pi j, so as not to have two different appearances of I, or sorry, this is from this to xj is what everyone had when I was looking through. You just take your tuple and you send it to xj, right? You just pick your jth coordinate. Cool. So yeah, that one was pretty quick. There's no proof necessary there. You didn't have to like show this was a topology again or was a basis again. It is for the same reason that the last one was. So that was fairly straightforward. I think just a lot of people didn't realize that they were supposed to do this part because that was part of the problem. Define the product topology for the infold product of the xi. The best of reasons. Because the book told me so. You don't believe me? I literally just read it. First of all, who is this they? No. Yeah, no, that was just like saying that's the set. Yeah, I'm at least part of the they, yeah. All right. So, okay. So I guess question: did you want to do 163 and 164 separately? Did you want to do? How did you? So the reason, right? Like I know some people kind of cited 164 as saying that 163 is true because of it, but the reason they were in that order is to develop some sort of intuition for 164 from 163, right? All right. Let's do 163. I know. I was just like, this seems. Yeah, I thought you begged the question a little bit on that one. Who is this Devon, Will? You can look in Discord for the spelling of his first name. All right. Are we really using Bach? All right. I'm leaving. That's fair. It is a class of abelian topology. By the way, I'm curious. What's your math background? / how did you come here? Okay, so we're looking at I cross I, and basically we want the standard topology as a subspace, right? So subspace of the standard topology of R2, or we want this to be equal to, I mean, we said kind of examine, but from the theorem that follows, we know that it's got to be equal to, so this is what we want to show, that it's equal to the product topology on I cross I, where I gets the subspace topology inherited from R's. subspace topology from standard on R. Is there a textbook? Yeah, not really, but I mean, Moncrief's is always a really good source. Yes, I mean, like, unless one of them wants to send you a PDF, like a good source, since you're not in the class and don't have to do the whole IBL thing. I mean, Moncrief's is a really good textbook in general. Okay, so for me, I think I did see a couple people kind of suggest 92, and I do think that's the way to go. Wait, is that guy one of us? Wait, who is abelian topology? All this time, I've thought this was someone. So no, he is someone else at Wabash. Devin, I didn't realize your name was abelian topology. I legitimately thought that you were some random dude since the first day. That's a cool name. Rip. Why is Jack just giving me the question? Oh, I hope that's in response to Rippy. I thought it was Devin. Man, that's fair. I feel incredibly stupid. All right, that's fine. I was really hoping that that was just some random grad student that was just like joining our class. It's all on you, Bork and Bork. Bork bin Bork. You're the only foreigner here in terms of not in our topology. All right. So right, 92 is the whole like take a basis element, show it's inside, or show that there's a basis element inside the other one that's inside. Here, I think we can even show that these are exactly equal, right? So we should look at like basis for each and see that these are really equal. So let's look at these. Igor Pak. That dude teaches in shorts. He's a legend. Okay, so I gave these names. So said BS, calm down, for the subspace topology, and then, you know, BP for the product topology. So I don't know exactly what theorem it is, but basically our basis elements for the subspace, right, we know look like, by the way, which of the bases do we want to use for R2? What makes the most sense here, right? We have the open balls and the open rectangles. Which one seems to make more sense to use? Yeah, rectangles for sure. So let's use the open rectangles. I turned my pen. So use the open rectangles for R2. We know they're equivalent, so rectangles make a lot more sense because they are the product of open intervals, right? So here our basic opens are basic opens inside R2 intersect I cross I, right? So it looks something like AB cross CD, cap, I cross I. Can I get kappas in the chat? Yeah, nice. Right, so here we have A is less than B and C is less than D. Cool. And then our other guys down here, right, this has the basis of, and remember, so we started with basic open sets and the product could be just open cross and open. But then we showed afterward, right, with just a little more work, it was like an extra step that you could actually do basic open cross a basic open. And so that was theorem 155, right? So by 155, this is like AB cross I cross CD cross I. Same thing. Okay. So are we good there? Do we see how to proceed? Yay? Nay? We're basically at the same step as last time. Is there some relation between these two things? As written? Yep. Yeah, exactly. So, yeah, this is a lemma here, sure. I mean, yeah, this is more general, right? So if you let A, B, C, oh boy, how do I want to do this? It's probably not worth it. I don't want to state it yet because I want more. I'm just going to do it in this case. So yeah, these guys are equal, right? So AB cross CD intersect I cross I. Oh, I do see what I need to write it as, right? So yeah, the lemma we'll get to in a second is that A, B, C, D are sets. Then A cross B intersect C cross D is equal to A intersect C cross B intersect D. And so basically these guys, you can just distribute the intersection here as such, and then 92 gives the result. Right, because not only did we find a basic open inside it, it's the same basic open, right? You've just like rewritten it. So like the basis elements are literally the same. Okay. Yep. Right. So I mean, they're all still in the same place, right? So here, as written down below, A and C are subsets of say X, and B and D are subsets of Y. And so like this is an X cross Y, this is an X cross Y, this is an X, this is in Y. So like this is an X cross Y. And the same thing up here, right? So like these are general intervals, so this is in R2, but then I intersect with this, so it's still in I cross I, and then this ensures it's in I, this ensures it's in I, so it's also in I cross I. Cool. Yeah, they do. They actually speak. It's amazing. No offense. You actually participated some, and you were very helpful in the review session. But yeah, it's a much more talkative class for sure. Uh, okay, so do we want to prove this lemma? I mean, we kind of talked through it. Yeah, talking is good. Asking questions is excellent. Do we want to prove this? Does it seem true enough? Okay, let's do it. So this really isn't too bad. So the way, I mean, you should be able to kind of eyeball what's going to happen, right? So like, if you're on this side, then you're simultaneously in both of these. So your first coordinate has to be in A and C. Your second coordinate has to be in B and D. So that's basically that direction, right? Um, and then similarly, right, if you're over here, then you're in A and you're in C. Oh boy, that was unintentional. And if you are in B intersect D over here, then you're in B and you're in D. So that's my proof really fast, but yeah, okay. So let's suppose XY is in this if and only if Yep. And then this is if and only if x is in A and y is in B, and x is in C, y is in D. And now we have x is in A intersect C, y is in B intersect D. And boom. Yep. Huzzah. Useful lemma. And again, not true for unions. So don't use it for unions. And we have a very simple example. Again, it was the 4 rectangles versus 2 rectangles thing, right? That's how this fails. And again, this is kind of a common theme, right? Like intersections are nice. Intersection of subgroups is a subgroup. Intersection of topologies is a topology. Unions of things, in general, it doesn't work nearly as nicely. Okay. So this might be useful moving ahead. So 164 is kind of generalizing this, right? That our subspace topology on, so if we have A cross B, subset of X cross Y, then our claim is the subspace top on A cross B equals product top on A cross B, where A and B get subspace topologies from X and Y respectively. So now that we've done 163 all the way through, how might one go about proving 164? I think in general this is probably, I thought this was the hardest one. Oh, sorry. I don't know if you love 94. Yeah, so I mean you could definitely use well no, but you have used 94 several times. I just found it interesting. Yeah, so I think you could use 92 and do basic open similar to what we did up here, right? So sorry, something's on my screen. I apologize for the sound. I probably should have muted myself. So what are our basic opens in A cross B with the subspace topology? You mean intersection? Yeah. Yeah. You said union. Yeah. Right. So this is intersect, what do I want to call this? I'm just going to say U, where U is basic open in X cross Y. So if U is basic open in X cross Y, then again, I can take it to mean a couple of things, but by 155, I can actually say that U is, how do I want to do this? Sure. How about U, sure, U1 cross U2, where U1 and U2 lie in bases for X and Y. E? Basic. What is wrong with you people? All right. Okay. Oh, I think this is why I didn't necessarily love. Okay, so would I rather do that? So let's think about what are the basic opens in the product? Okay. Racist? That's greatest. Gratis? All right, can we do topology? Not meme. Did you just unmute yourself just to laugh? All right, fine. I'm gonna take the wheel like Carrie Underwood let Jesus do. Never mind. All right. So these guys, right? So if you have like a basis for X and Y, then your basic opens in the product would be a product of basic opens from A and B. And so a basic open in A is U1 intersect A, where U1 is basic open in X, and same in B, say U2 intersect B, where U2 is basic open in Y. Right? So basically, you get the basis of the subspace by just intersecting with basis of the big space. So now you can use what Devin called his lemma, right? So we can just basically do the same thing. I mean, we said U was this product, right? So we know by our lemma that A cross B intersect U1 cross U2 is equal to U1 intersect A cross U2 intersect B. And so these are exactly the same. So the basis elements are the same. So the topologies are equivalent. Usually we use the last name, I think, but you can be, like share. All right. Questions? Cool. Excellent. We're quickly approaching the really cool pictures time. I'm excited. Okay, so Hausdorff. Yeah, this one had very mixed results. So it's important, right? So Hausdorff is all about if you have two things that are not equal, you can find open sets around them, right? That are disjoint. So here, if we want, so here we have x and y are each Hausdorff, then their product is Hausdorff. And again, since we can always prove things by example, just a bit of intuition, right? Like we know R is Hausdorff, we prove that. R2 is also Hausdorff, and that should make sense because, we could separate two things. Basically, like one of the coordinates has to be different, right? And then you can separate in that coordinate is essentially what's going on there, right? So if you have like a picture and say like they're the same y coordinate but different x coordinate, so you have like these 2 points. Well, the point is if I restrict myself to just my x coordinate, I can find my open sets down here that are different. And so then when I cross with like an open rectangle, say I cross with this guy, I get this, and then I get this. Right, so this is the idea. They must differ in one coordinate. If they're different, they might differ in both, but you don't need that much. The second they differ in one, just leverage that fact and you get your result. So let's just take 2 points. So say say x1, y1, and x2, y2 be in x cross y with x1, y1 not equal to. So you should always write, like if we're talking about Hausdorff, we want to start with two things that are not equal. So we've got to state that. And then, like I said, only one coordinate really matters, right? You could, yeah, I mean, to find disjoint open sets around them, you need them to not be equal. And so it may not be true that they're not equal in both coordinates. So it has to be true in one, and without loss of generality, let's say it's the first coordinate, like the picture above, right? So this would be like my x1, my x2, and then this is y1 equals y2 here. Okay. Can you rephrase that? What do you mean? Oh, so I mean, you're just saying it's like a 1-point space? Then yes. Yeah. Yeah, for sure. I think that's basically the idea. We're not exactly like fixing something. It's more that well, you only know what to fix after you know which ones are not equal. Right? So like once I know they're not equal in this coordinate, then I don't really care about my y coordinate. But I can't fix from the start. Okay, cool. Yeah. So since x is Hausdorff, there exist U and V open in X such that X1 is in U, X2 is in V, and U intersect V is empty. Okay, therefore right? Like then u cross y and v cross y have to be empty, right? Because they can't share their first coordinate. Those are disjoint, and so it doesn't matter if they have the same y coordinate, right? So basically x1, yikes, x1 is in u cross y, x2 is in v cross y, and u cross y intersect v cross y is empty. And if you don't see why that's empty, you could, of course, again, apply that lemma and see that this is u cross v cross y. I mean, it's y intersect y, but that's y. And we know that this guy is empty. All right. Cool. So yeah, basically, Hausdorff holds under products. Now, doing it for an infinite product is actually hard. So that's what we call Tychonoff's theorem, and that will probably be, or sorry, no, that's compact. Product of compact is compact. What is product of Hausdorff is? No, that actually should work out the same. Never mind. Ignore me. All right. So 167, this is where I definitely want you guys to speak up if things aren't making sense, because I want to see how you're picturing these things in your head. So actually, yeah, if you guys want to like chime in on these, please do so. So number one, we have this, right? So basically we're saying that these 2 points are equal. So we're gluing our 2 points together. What do we end up with? Yeah, a circle, right? So we're only gluing those 2 points. Everything else stays the same. So you start with this and then boom, we go around. Okay. This one is definitely a little harder. Look, man, no, yeah, it is a cone. Right, so we're wrapping around this bottom, right, to glue this. So basically you get the circle from above, and then you have to see like what's happening up here. Well, we're gluing this edge to this edge. So yeah, you're exactly just take your triangle and then you just wrap it around so that you have a circle on the bottom. So yeah, we get a cone. It's good. Yeah. Cones are very nice little contractible spaces. And by the way, right, this is a hollow cone. There's nothing inside, right? Because this is just like a two-dimensional thing. We don't get 3 dimensions suddenly. Because Will, I think you asked about like going from 2 dimensions to 3 dimensions yesterday. I wasn't exactly sure what you meant, but like I think that's one of the things, especially with the last one that we'll see, number 6, where you can't like add a dimension. What? I mean, like, sure, yeah, it could be. I think it's not a line. Um, well, that's not necessarily what it means to be a manifold, but yes, they are all manifolds. Manifold means you locally look like Euclidean space. So basically, if I zoom in, right, this is a 2-dimensional manifold, because if I zoom in, even though I draw my cone in 3 dimensions, if I like look at this little spot in here, this looks exactly like the plane, right? If I zoom in really close. And that'll be most important on the 4th one, because that actually has to lie inside R4. But notice, like in number 1, right, you don't have to embed it in like a bigger, well, yeah, I guess, sure, R to R2, okay. But like, you can be a manifold, like R is a 1 manifold, and it doesn't have to embed in anything bigger. It could, but it doesn't have to. But yeah, like locally, this guy looks like R, right? Okay. What's the next one? So here, yeah, and I think that one seemed to go pretty well. You guys seem to get the torus pretty well. Right, you just take your sheet of paper, you fold it, now you have like a cylinder, and then you hook the cylinder together and make a donut. Right. And so one of these guys is going to be like your A, and then the other one will be your B. Probably should have drawn those in different colors, but what are you going to do? Okay. So the next one, so notice here, we are only gluing one side, right? We're not doing anything with the top and bottom. What happens here? Yeah, and I'm not going to draw that because I don't trust myself to do so. No, I don't honestly think that I could. I could Google it and then I could probably draw it, but it doesn't seem worth it. But yeah, essentially, I don't have a nice cut up piece of paper. But like what you're doing, right, is you just have your paper, you come up here, but then you twist this and then put it there. So you have this twist instead of just making like a loop. So it's no longer like cylindrical or like an annulus, I guess, if you thought of it as long and thin. You have this twist, and so there's actually like there's no side to it, right? There are not two sides. There's no like top and bottom or inside and outside. There's only one side. You can just keep traveling it around. Yeah, if you cut like a strip of paper and do it, it's kind of cool. It's an activity that we always did with middle schoolers when I was in grad school. They enjoyed Mobius strips and like linking them together and stuff. Correct. Correct. Both of them are non-orientable, and that's basically the complicated way of saying. Yeah, I can hear what. Yeah, it's the complicated way of saying there's no inside or outside. Right, because an orientation is exactly saying like, I choose a direction basically and say like this is my up and down or this is my inside, my outside. And so not able to do that means you don't have this. Okay, so then we have the Klein bottle. So this one I just kind of told you to look up because if you haven't seen it before, I mean, you're not going to like guess it, and it's really hard to do because you actually need 4 dimensions in order to like glue this thing together this way. So I would be impressed if you managed to do it. Yeah, that is very much a Mobius strip. Dope. Can you now do me a Klein bottle, Nick? Nice. um, all right. So the Klein bottle, how do you guys think of this, by the way? Do you have like, obviously, yeah, you can Google that. Have you guys like, you should look up a YouTube video. Think of what? Yeah, I mean, there are a lot of YouTube videos. Okay. Nice. But yeah, basically, you should look up a video. Essentially, what you do, right? So, like, if you glue the bees together, right? So these are the bees. If you glue the bees, you get a cylinder, and then you basically want to do the Mobius strip thing, right? Where you want to invert the orientation on one of the edges, right? You want to do like a twist and then glue it. But to do that, you actually have to go in through the cylinder and go back up and then come around, basically. And so like there is no hole in the cylinder in order to do that. And so you need 4 dimensions essentially to have enough room to actually go through, come back up, and be able to twist like that. Yeah, awesome. Oh, sorry. Yeah, B's are supposed to be the same direction. Jeez. I didn't realize I screwed that up. Sorry, B's are the same direction. If B's are not the same, I don't know what that means. Oh, you just mean like a Mobius strip cross a Mobius strip? Gotcha. I don't think it's called that. Ah! Question, Jack? It's called the real projective plane. You should look it up. Watch that video. Watch the video in Discord. After class, but watch that. I'm not going to be able to explain it better than that, for sure. Okay. Yeah, it without that, like what I do with my hands is not going to be better than what they do. Okay, so then the last one is kind of a weird one. So you start with a disc, right? So this is actually full. I guess all of these were technically starting with these. Probably should have done this throughout. Oh, I didn't see how much, but I didn't really watch the video. Is it? That's fine. Yeah. Devin will find you a good link. So if we glue the boundary, the whole boundary together, what do we get here? It is a sphere. Yeah. Basically, yeah, you just start with this and then you come together, right? You just kind of make, not really a fist. Maybe this is better. You just kind of bring the boundary like that. So yeah, you get a nice sphere. Making a taco and then blowing it up. Yeah. Yeah, that works. Oh, that is great. That is, yeah, I really like that. I really like that one. That's cool. All right. So, yeah, this is just kind of like, I said folded tortilla. Yeah, I guess. It's not so much a pierogi, right? Because you actually like pinch the edges. You have like a little extra, but I guess, yeah, it's fine. All right. So, quotient topology. This is basically some motivation for it. Right, so remember cosets. We thought of that as, right, so like quotient groups. We glued, and it was obviously much less visible than this is, but we glued cosets together. And cosets were defined by an equivalence relation, right, to get a new group. that was our way of dividing in groups. And so this is kind of the same thing, right? So here, quotient space, you glue together pieces of your space to get a new space. But this isn't obvious, right? Like here I said cosets, which is very like descriptive. I mean, I know what a coset is. I tell you exactly what you're gluing. What are these? What pieces do I glue together? And so what we want to do here is give an idea of, it still needs to be a topology too, right? So like, I mean, sure, I can make these gluings, but like what is my topology on this sphere, right? Like I have a natural topology on the sphere. I could do like the subspace topology from R3, which gets the product topology from like R and stuff. But that's not the topology you're going to get, right? Somehow it should inherit a topology from the thing it's coming from, right? It should inherit a topology from the disk. And so this is how we kind of motivate defining the quotient topology. So you're really looking at like some sort of projection, right? This gluing in some way is like a projection. It's a surjective map. And then you want to lift back up and see, okay, what are my open sets up top? Those things, right? So like the things down below will come from open things up above is the idea. So quotient topology. This is in general, I guess, one of the more challenging topics, especially once you do like homeomorphisms using quotients. It's where you kind of get into some universal property kind of stuff, although I wouldn't necessarily phrase it that way. Okay, so here we are on what, page 45 is where we define this. So this definition 168. So I want to kind of walk through this and talk about what exactly is going on. So we've got X as a topological space. A is some set, so we're going to make it a topological space, but right now it does not necessarily have a topology on it, and it's not a subset of X necessarily, right? This is just some set. And then we want some sort of, again, it's not a projection in that like X may not be a product, and so it's not just like taking a coordinate, but it is a surjection, and you want to think of it as kind of projecting down onto A. So P is a surjection. Then I guess I have a more nicely written up thing, I feel like. Yeah. So we define a topology on A called the quotient topology. On A as follows. Right, so to have a topology, all I need to know are what are my open sets, right? So U is open in A if and only if its preimage is open in X. All right. So if you look up above, let's look at like example 1 just a little bit here. All right, so we've got this guy goes to this guy. Then like what's an open set here? Well, I look at its preimage, right? So if I do this, then I get, who knows, let's say I start here 0 and I'm going clockwise to 1. I'll say this is 0 to 1. Why not? It's some interval, who cares? So this is something like this. Well, that's an open set inside 0, 1, right? So yeah, that's open. And in general, right, like if I include a point here, then this would look something like this, not open. So this is not open. And then the interesting ones would be something around here. What do these look like? Well, this looks like this union this. Is that blue set open or closed in my X over here? Why? Boom, love it. All right, nice. Yeah, so we're good including the endpoints. Yep, so this is open. And so this is open, which again, we would kind of hope it's like an open interval on the circle, but yeah, we can actually justify it. So this is how this is defined in general. And in this case, so we have some just terminology. So P is called a quotient map here. And now if I give you a surjection and like you already have a topology, you can like determine if it's a quotient map. So P is a quotient map if and only if P satisfies two things. One, it's surjective. And if U is open in A, if and only if. So I'll just maybe put brackets around, like it's this whole statement. And if U is open in A, if and only if P inverse of U is open in X. Has to satisfy both of these things. Okay, so basically it's a quotient map if you get this correspondence between open sets and your surjective. And so as we have defined it, so as defined, right, like if you start with A as a set where it doesn't have some topology already, and like you define your open sets like this, like P is automatically a quotient map. But for instance, right, if I start with this circle, I could use the subspace topology from R2, right? And so I could say like this is already a topological space. And then I already know what my open sets are here. And so in that case, right, I would have to check this statement, right? Because I know what open sets are in A if A is already a topological space. Okay. Do we see that distinction there? That can be somewhat challenging. So basically, if A is a set and gets the quotient topology from P, P is a quotient map. So that's like automatic. And then if A already has a topology, so again, like it has to be surjective either way. So I guess I should say like if P is surjective, but that's like assumed in the quotient topology. If A already has a topology, you have to check 2. Since you already know what U open in A means. Right, so you have to see that the definitions match in that case. So that's a little complicated. We'll get into that more with the example in 172. I kind of give you exactly this. Basically, you see this one and you see this one, and then you'll see that they can be different. Yeah. So you can basically have P not be a quotient map, but if you took it to be the quotient map, you defined your topology that way, then you can get a different topology. And then our other terminology is, so A is the quotient space. With the quotient topology induced by P. So here's that word induced again. Right, so induced, similar to inherited, right? So inherited from P, induced by P, you're just kind of saying like one's kind of more passive voice and the other's more active, right? P is doing the action or the action was done by P. That's basically the only difference there. Well, so like you could have many different quotient maps, right? So like you could have many surjections that would define different topologies. So this is the one specifically inherited from P. So very much that the open sets are the things where P inverse of U is open, as opposed to say like F inverse of U is open. Correct. Okay. Well, we are out of time. But the first star that looks like you were okay, basically. Oh, wow. Yeah, no, that's completely unintentional. So I guess we can close here unless you want to see like this example 170. If this seems really confusing, we can do that really fast. Otherwise, we should probably close up. Um, and unfortunately, Westfall actually made us do a department meeting, so I don't actually have I have like 10 minutes for office hours, and then I'm free basically except for 3 to 4 this afternoon. So if you guys want to ask questions this afternoon, I'll be mostly free because we're apparently doing meetings still, which saddens me. That's good. Yeah, I mean, we'll later see that there's like an equivalence relation definition as well. Yeah. What's up, Nick? Gone. Okay. Well, I'm gonna go ahead and cut stream then, but I'll be around for a few minutes. Cool. Bye bye.